Yes, please type your attendance there in the chat box. So from today onwards, we can have regular class finally. Me, Dr. Vanteya, and Dr. Monpuya, we are all engaged in the examination committee. So there are several works here and there. We are so disturbed because of this UG examination. And one of you is having this workshop this week. So I don't know if I can start the offline practical class this week. Let's try to cover as many theory topic as possible this week. During your practical class also, I will cover your theory class. I will take your theory class. Tomorrow, we have semester examination, that is offline examination. So again, tomorrow I will be a little bit busy. Other than tomorrow, I will be more or less completely free. So whenever you don't have class, you just let me know, and I think I can take class. So I will try to cover the topic, the syllabus, as much as possible. And regarding the reading material, I will just give you my PPT, and most of the things are written in my PPT for the remaining part of the lecture also. The previous lecture also, I'll just give you the PPT. Most of the things I've written. And you already have the lecture video, which is available in the YouTube. So it should not be a problem for the reading material. You can just go through the PPT, which I will give you, and the whole PPT I'll give you. And we will try to take as many theory classes as possible. Next week, we will have offline practical class. This week, we will cover, if we cannot complete the syllabus also, we will cover as many as possible. And whatever we are going to do next, it's just so simple. If you read it also, you will understand it. So nothing much to do. So here we have talked about the components of our display device, that is cathode ray oscilloscope. And we have said that cathode ray oscilloscope consists of CRT. CRT means cathode ray tube. And we have described the components of this cathode ray tube and the working of this in direct heating of the cathodes. And the cathodes generates those high energy electrons. And those high energy electrons are focused using this control grid. So, and also this using focusing anode. And there is this accelerating anode, and that helps in accelerating the electrons, the free electrons towards this, the display screen. And we have described how the vertical deflection plates function. And depending on the signal which is supplied to the vertical deflection plate, depending on the signal which is supplied to the vertical deflection plate, your cathode ray, that is your electrons which are traveling in this direction, it will be deflected according to that. And once it is deflected through this deflection plates, it will pass through it, and then it will pass through these horizontal deflection plates again. And the horizontal deflection plates I will discuss in a few minutes. So after passing through the vertical deflection and the horizontal deflection plates, depending on the signal which is supplied to these vertical deflection plates and the horizontal deflection plates, those cathode rays, the high energy electrons, they will strike the screen of your CRO. And this screen consists of a certain phosphor. Phosphor material means when you have inelastic collision with electrons, that is when free electrons strike this phosphor material, high energy electrons, as it strikes the screen, there is an elastic collision. Inelastic collision means energy is transferred from this electron to this energy is transferred from the electron to the phosphor screen. And wherever the electron strikes, though the phosphor material will emit light. So depending on the signal which is supplied to this, the vertical deflection plates, and the voltage supplied to vertical deflection plates and horizontal deflection plates, your electron beam, as it strikes, your electron beam can strike different portion of your cathode ray tube. So as it strikes different portion of your cathode ray tube, and depending on the signal, it may trace out the sinusoidal signal, or it may trace out the triangular signal, or it may trace out a rectangular signal, or it may even trace out some arbitrary noisy signal also, depending on whatever signal you are giving to these vertical deflection plates and the horizontal deflection plates. And we have discussed about this sensitivity also. We have calculated that this is the deflection sensitivity. This is the deflection sensitivity, and it is defined as the voltage required per unit deflection. So why is the deflection and all? I think we have concluded up to this, or otherwise you can. I think I have concluded up to this. So the deflection sensitivity is depending on your accelerating what is that? Your accelerating voltage. VA is your accelerating voltage, right? So your accelerating voltage, and D is the separation between the deflection plates, and the length of the deflection plates L, and your R, that is the distance of the screen from the deflection plates. So depending on all these parameters, the deflection plate sensitivity can be controlled in the CRO. Now, when you are having a certain signal from your measurement instrument, like your sensor and all, as I said, that signal is first, that signal as detected by your sensor or your transducer, it will be first converted into electrical signal. So suppose you are detecting some vibration, vibration and all using your sensor, let's say your earthquake sensor, and that is non-electrical signal. Actually, it's just a mechanical vibration. So such kind of mechanical vibration, when it is in sort of contact with this sensor or your transducer, so it will convert such kind of vibration or pressure into electrical signal. So this is the kind of material I'm also working on as a research. So we are trying to develop some kind of sensors also. And also in my case, one of the research paper we are working on is gas sensors. So suppose in a certain region, suppose there are certain gases, so that sensor, when it absorbs those gases, the electrical property, the conductivity or the electrical signal passing through the material will change. So the change in electrical signal will be the information that such kind of gases is detected and all. So once it is converted into electrical signal, the signal will be processed. It depends on whether it's your device is a analog device or a digital device. Your display device is analog device or digital device. Like for example, CRO is an analog device. Analog device in the sense that whatever signal you are feeding to CRO is some kind of continuous AC wave, or it could be a triangular wave or sinusoidal wave. So this CRO will receive analog data only. It receives analog data only, and that analog data, that kind of small signal is supplied to the deflection plate, and when it is processed through the deflection plate, that will result in a display of signal on the phosphor screen of your CRO. But your computer system and all is a digital system. So like I said before, when you are using a digital display, you have to convert analog signal into digital signal. So a computer information is processed, computer information is processed only in a digital signal. So analog signal, CRO is one of the analog signals, analog display devices. Okay, analog display devices, cathode ray tube is. So before, let's say this is your deflection plates. So this is something like, this is your vertical deflection plates like the one I have shown before in a previous lecture. These two plates are the vertical deflection plates, and these two plates are the horizontal deflection plates within the cathode ray tube. So your input, whatever input you detected from your sensor, it is first supplied to the vertical amplifier. Okay, it is first supplied to the vertical amplifier. So this vertical amplifier will amplify that weak signal and pass it on to this vertical deflection plates. It passes on to the vertical deflection plates, which is connected between ground and this. So this vertical amplifier in the CRO, you can even control it. You can even control the vertical amplifier using what is that? I just forgot the term. Anyway, I will show you the CRO. Yeah, here is here this vertical deflection, vertical amplifier and all, you can control it using this. You can control the signal, how large you want to enlarge, and all those things you can control it. Yeah, so it is supplied and to these vertical deflection plates, and this will feed whatever information to be displayed to this vertical deflection plates. And in addition to that, this signal, the same signal coming out from this vertical amplifier, the same signal coming out from this vertical amplifier, in addition to feeding to the vertical deflection plates, it can be used as an internal sweep. Internal sweep means like in a CRO tube, suppose you are giving your signal only to the vertical deflection plates. Depending on the signal variation, your cathode ray or the electrons may strike the middle spot, or it may strike upwards, or it may strike here, or it may even strike somewhere here. And depending on the signal, the glow may travel up and down only. The glow may travel up and down only. But when you are going to display it in a CRO, if you want to see the frequency of the signal and all, what you need to do is that same signal, vertical amplifier signal coming out from this vertical amplifier, it can be connected to trigger sweep generator. Sweep generator means this trigger sweep generator, what it will do is it will take the input it will take the input from your vertical amplifier. Okay, it will take the input from your vertical amplifier. After taking the input from your vertical amplifier, it will convert such kind of input into this kind of sawtooth. It will convert sawtooth. So basically this trigger sweep generator is a sawtooth generator. It converts this kind of input, square wave input, into a sawtooth. Okay, so when you supply a sawtooth wave, like for example, let's say this is time axis. So between this to this, your voltage is increasing almost linearly. Between this to this, your voltage is increasing almost linearly. And then in this sawtooth generator, and then it drops down. And then the voltage is increasing almost linearly in this interval. Okay, the voltage is increasing almost linearly in this interval once it converts into a sawtooth. So that kind of voltage, linearly increasing voltage, is given to this horizontal amplifier. So the horizontal amplifier will result in a kind of something like this. Once it is amplified, it will result in some kind of linearly increasing voltage. Let's say this is your voltage. Let's say this is your time. Horizontal amplifier will even amplify further. So it will convert into this kind of linear voltage, linearly increasing voltage. So what happens is that when you apply linearly increasing voltage to these horizontal plates, so the other end of the horizontal plates is also connected to ground here. Other end of the horizontal plates is also connected to ground. This is a ground connection. So one end of the horizontal plate, when it is connected to this kind of sawtooth signal, linearly increasing, drop down, linearly increasing, drop down. So between this interval, what it is going to do is that it will increase the voltage applied on this. So as it increases the voltage applied on this, what will happen is that instead of the uh, cathode ray beam, when it strikes this, instead of the cathode ray beam going up, going down vertically, depending on the signal given here, depending on the signal but given here, the vertical reflection plates will only enable the cathode rays to travel up and down. But once you supply this kind of sawtooth wave here, linearly increasing signal here, this voltage will gain, these electrons will also be influenced by, these positive plates here. So as it is influenced by these positive plates, these electrons also will travel horizontally also. So instead of traveling up and down, let's say while it is traveling up, it is also having a horizontal voltage. That means it will trace something like this. So what happens is that instead of traveling up and down, depending on the signal which is given to this vertical deflection plate, the other end is grounded. Once you have a sweep signal here, this is also grounded. This is also grounded. This is connected to ground. This one is also connected to ground. When you supply this kind of linearly increasing voltage here, V versus T here, sawtooth, instead of traveling up and down, as it travels up, it is also deflected in this direction. So it will trace something like this. It will result in tracing this kind of waveform. Okay, it could be depending on the signal received from the sensor. It could be triangular wave, or it could be square wave, or it could be sinusoidal wave of a certain frequency. Certain frequency means like this kind of thing. So because of this horizontal sweep, which is the signal which is given by your sweep generator, linearly increasing voltage, instead of the electron beam traveling up and down, it will trace on the screen. It will trace certain kind of waveform on the screen. So that is called internal sweep. This is the most common way of using a CRO. So whatever signal we are using in a CRO, we have an option of having internal sweep as well as external sink. External sink is you are giving certain external voltage to the sweep generator. So this external voltage will be used to sweep your signal along the horizontal direction so that it can trace a kind of waveform. Instead of moving vertically and downwards, it can trace this kind of waveform. So this kind of external voltage signal can also be used, but in most common cases, this kind of cathode ray oscilloscope, it is operated using this internal sweep. So the advantage is that this internal sweep signal is coming from your input signal. Whatever input data information you are getting from your sensor, it is supplied to this vertical amplifier. The amplifier signal is given to this and also given to this triggered sweep generator. So that converts your input signal itself into this kind of sawtooth wave. So the sawtooth wave will result in tracing of the cathode rays on the screen of this cathode ray tube. So depending on such thing, you can have this kind of wave. So this is the horizontal control. For the horizontal control, here you can choose different voltage per division. So the time per division, sorry, you can choose time per division. So in a CRO, there will be a what is that? Yeah, this kind of division like this. This is called one division, and between this is another division, this is another division. So this axis is your time axis. So along the time axis, you are supplying your sawtooth wave, which is coming from the internal sweep. Internal sweep means which is also a part of your vertical signal. A part of your vertical signal is converted into use as an internal sweep, and which generates a sawtooth wave. and this axis is called the time axis, and the vertical axis is called the voltage axis. Over here you can control the volts per division here. One division, how much volts it will carry. Okay, one division. Here you can have a, you can select, you will operate with this CRO. I think many of you have seen it also. You can select 0.4 volt per division. If you select 0.4 volt per division, means out here this one division is equivalent to 0.4 volt. Okay, if you select 0.5 volt per division, something like this, suppose this is the signal you have on your CRO screen. If you look at this, this is one division, this is another division, two division, and this is a half division, this is a half division. So there will be three divisions. Peak to peak, peak to peak, you have a three divisions. So number of divisions in the vertical direction, that is the peak to peak signal here, is three divisions. So if you select in the vertical attenuator, if you select in a vertical attenuator 0.55 volts per division, then the peak to peak voltage value will be 0.5 volts per division into 3 division, that is 1.5 volt. So like that you can calculate, you can study the like the amplitude of the signal also. Now you can even study the frequency here. So how you're going to study the frequency is that you have to, on the horizontal attenuator, that is the horizontal scale out here, you can select the number of, you can select the time per division on the horizontal scale. So by selecting the time per division here, you can record the time per division, how many time per divisions are there, and how many divisions per cycle. So this is one cycle of a wave, right? This is one cycle. So another cycle it will repeat again, another cycle it will repeat again, something like this. So in one cycle, how many divisions are there? In one cycle, you will find that one division, two divisions, three divisions, four divisions. So there are four divisions in one cycle, right? Four divisions in one cycle. And if you are the attenuator, if you choose your time per division as 5 millisecond per division, so it will be something like 5 millisecond per division. So it will be 5 into 4 is 20 milliseconds. Now the frequency is the frequency of your signal is 1 upon 20 millisecond. Okay, so 1 upon 20 millisecond will be like 0.4, right? 1 upon 20 is 0.05, sorry, 0.05. Milli means 10 to the power minus 3 seconds. So it will be 10 to the power 3 hertz. Okay, per second is hertz. 1 upon second is 1 hertz. So millisecond means 10 to the power 3 hertz. Okay, 0.05 10 to the power 3 hertz frequency. So like that, I think this is something you can operate with CRO. I will explain with the CRO also how it is to be operated next week. So with that, we can stop. Now let's discuss this regulated power supply. So a regulated power supply is very much essential for several electronic devices, mainly due to the fact that, like, your semiconductor material employed in your devices and all, they need a certain kind of fixed supply. For example, if you are talking about, let's say, amplifier, in your amplifier also, I think most of you are familiar with an amplifier. In an amplifier, usually we use a transistor. Amplifier, we use a transistor. If you remember, what is that, RC coupled amplifier also. In RC coupled amplifier also, we have a transistor with an emitter, base, and collector. And in order to operate this transistor, you need to provide a certain kind of fixed biasing here. So fixed biasing means the biasing voltage between emitter and base should be fixed. The DC voltage which is given to this emitter and base should be fixed. And also the biasing between your collector junction and the base should also be fixed. So for that, in RC coupled amplifier, you are going to need a certain kind of constant voltage. constant voltage is needed to properly bias your transistor. If the voltage given to such kind of amplifier fluctuates, if the DC voltage given to amplifier fluctuates, then the biasing between emitter and base will change randomly, and you will not be able to get a desired amplification process. Okay, sometimes depending on the emitter base biasing value, the amplification may be large and maybe low like that. So most of these semiconductor devices, they require a certain kind of fixed biasing voltage. And transistor is the main component of your computer memory devices. Also your processor also consists of large quantity of transistors and all. So all those transistor element, the on and off state of a transistor will carry digital information. Like the on state will carry digital information as 1, the off state will carry digital information as 0. So your computer memory is also based on such kind of transistor device, whether it's in an on state or off state. So thousands of transistors are embedded in a small ICs of your processors. So these processors, or even your memory device, your hard disk and all, they works on all these transistors. And in order to properly operate such kind of electronic device components and all, you will definitely need a certain fixed biasing voltage, okay, fixed DC supply. So without this fixed DC supply, most of your electronic devices will not work. Now, so the main reason why we are going to need a regulator is we require fixed current. We require fixed current, which does not change, Okay, so we can use a battery for that also. Battery gives you like battery gives you, if you remember, there is a pencil battery and all. It gives some batteries are giving 1.5 volt, some batteries are giving larger batteries are giving 3 volts and all. So pencil batteries are giving certain kind of fixed voltage. Okay, so but in many of the ICs, we require 5-volt logic, because your transistor, your computer memory is also working on 5-volt logic. So when it gives out 5 volt as the output in the collector here, so if you remember, this is a transistor. So in this transistor, in the output, if you have a 5 volt, the logic value is considered as 1. And if the output in the collector is 0 volt, then the logic is taken as 0. So the binary information is either 0 or 1, but that is either 0 volt or 5 volt. Okay, so other than this also, many ICs are requiring a certain kind of fixed voltage. Okay, certain kind of fixed voltage. So for that, we need to prevent any fluctuation of the voltage. And so the voltage regulator is one of the most important component of your power supply in order to provide a fixed voltage. Also, you cannot use a battery, because battery will continue eventually drain out, right? Battery will eventually drain out, so you cannot rely on a battery, external battery system and all. So you need to have a continuous power supply, DC supply, to properly operate your electronic devices. So IC 7805 is one of the voltage regulator IC. Okay, so it's one of the IC78XX family of voltage regulators. So depending on this 780, let's say 9, so it means it's a voltage regulator which can give out 9 volt. So here IC7805 means it's a voltage regulator that gives a regulated output of 5 volt. So IC7805 is like this. So this is one of the most commonly used IC7805. So it's a 3-terminal device. And here, if you look at this side, one side on the left extreme is taken as pin number 1, part identification number 1. This is called pin number 1. And the middle one is pin number 2, and the rightmost is called the pin number 3. So it is manufactured by Texas Instrument and also on Semiconductor ST Microelectronics, Diodes Incorporated. So a number of companies are manufacturing these ICs 7805. So IC 7805, the IC rating. So whenever you work with a certain ICs in your electronic device components and all, what you need to know is the IC rating of the particular IC you are working with. So the IC rating of this IC 7805 is it can take input voltage from 7 volt to 35 volt. Okay, so if you feed DC voltage, or if you feed certain voltage above 35 volt, this IC 7805 will burn. It will overheat and it will burn. Okay, so the current rating means the maximum current that can pass through this. The maximum current that can pass through this IC 7805 is 1 ampere. So beyond 1 ampere current, your IC 7805 will be damaged. So you have when you are going to use this kind of integrated circuit, you have to know the power rating or the IC rating of this. So it cannot cross beyond 35 volt, or it cannot drop below 7 volt, whatever input you are giving. Okay, so the output which is taken from pin number 3 here, the output taken from pin number 3, it can vary between 5.2 volt and 4.8. So even though IC 7805 is considered as having fixed output voltage of 5 volt, fixed output voltage of 5 volt, there can be a certain limit of error, that is 5 point, it can go up to 5.2, and or it can be dropped down to 4.8 volt, not beyond that. So there can be a certain small fluctuation, but this minimal fluctuation will not harm your electronic device. So yeah. The input is supplied to this pin number 1. So I've discussed that. And also there is this thing called a need for heat sink. Okay, a need for heat sink to dissipate heat. Suppose I think we can explain from here. Suppose in this IC 7805 voltage regulator, this is the formula for heat generated. This is the formula for heat generated. Heat generated in that IC 7805, the formula is given like this. Suppose your input voltage here is, let's say 15 volt. Okay, input voltage here is 15 volt. So it gives out 5 volt, isn't it? It gives out 5 volt. And if the output current required in your device, if the output current required in your device is 0.5 ampere, so it will calculate the heat generated with this formula. Input voltage is 15 volt, and the output voltage, usable output voltage given out is 5 volt. 15 minus 5, 10 volt. So 10 volt will be the excess voltage. The excess voltage, 10 volt, will be the excess voltage that is not supplied to the output section. Okay, so here you are giving 15 volt to this input, and you are taking out only 5 volt as an output from this device. So the remaining 10 volt, it will be an excess voltage. So where will that 10 volt go? 10 volt will be converted into heat, because you are not taking out that 10 volt, or you are not connecting that 10 volt to the output circuit. So the excess voltage will be circulated around this IC as a excess voltage, and that will have to be released as heat from the surface of this IC 7805. So for that, usually all the most of the time, not usually, this kind of ICs, they are connected with this kind of metal. I think you can see here, this is a metal block. So this IC 7804 is over here. This IC 7804 is tied to this large metal with a large surface. So whatever excess voltage will be converted into heat when this IC7805 is in contact with this metal, it will conduct heat directly to this metal surface, and from this metal surface, which is having a large surface here, it will radiate out the heat. It will radiate out the heat. So therefore, it will just give out the extra 10 volt as a waste. Okay, heat waste. So heat waste. So the actual heat waste in this case will be, if the output current is fixed at 0.5 ampere. So extra 10 volt into 0.5 ampere, this will be 5 watt. 5 watt amount of electrical power will be given out. 5 watt amount of electrical power will be released as a heat waste. Okay, so depending on the amount of heat waste that will be generated in our circuit, you have to choose appropriate heat sink. Also appropriate heat sink also is required. How large this there can be multiple type of heat sink, so you can even choose a larger heat sink. Also you can even choose smaller dimension also, depending on how much amount of heat energy you expected it to be wasted from this IC7805. Okay, so here you see that the actual amount of usable power will be the 5 volt power which is connected to the output, and the current in the output circuit, that is 0.5 ampere. It will be 2.5 watt. Only 2.5 watt is the usable power. So the output, the power wasted here is 5 watts. So you see that twice the energy which is actually utilized is wasted here also. Okay, so now if you supply 9 volt here to the input section of this IC7805, then the amount of heat generated or as a waste will be 9 minus 5 into 0.5, which will be 2 watt only. So 2 watt energy will be wasted again. So in a way, this IC7805, it does not have any means to convert such kind of excess voltage into usable voltage. So it is not a very efficient IC when you are considering efficiency of usage of your electrical power. Okay, so it will just give out or just dissipate as a heat whatever excess voltage you are giving. Because this IC7805 can only give out 5 watt as the output terminal here. So in the output terminal here, pin number 3, it can only gives out 5 volt. So depending on the current, the desired current in the output section, the excess signal, the excess voltage given to this pin number 1 will be wasted. Yeah, so this is just a simple thing only, nothing much to understand. And this is the schematic diagram of IC7805. So you don't need to memorize this schematic diagram. Only you need to know how this IC7805 has to be connected, and how it works and all, the power rating and all. These are the things you need as a if you are going to repair your power supply circuit, or if you are going to repair your power supply circuit in your devices and all. So only you need to know the operation of this IC7805, the power rating and all. So this is for the designer of these ICs. So for the manufacturer of these ICs, you are within this IC, you are having I think 19 transistors here. Okay, you are having 19 transistors here. So this Q means transistors. Just a minute. What happened? I don't know if it's still visible. Yeah, I think it's still visible. So you can choose. So within such a integrated circuit, within